So imagine you're writing code in 2026, right? Your compiler is just so advanced, so mathematically rigorous that it can practically prove your application will never crash in production.
Oh, yeah. You basically feel like a wizard.
Exactly. You feel invincible. But then you try to take, I don't know, a 5-letter word and make it lowercase.
And suddenly you hit a wall.
Right. Suddenly you find yourself navigating this absolute memory labyrinth from the 1990s just to get a lowercase letter.
It's the ultimate paradox with, certain legacy languages. You've got these space-age safety guarantees sitting right on top of a foundational data structure that, well, it belongs in a museum.
It really does.
Yeah.
So, welcome to the Deep Dive. Our mission today is exploring that exact friction, that very real tension between legacy language design and modern coding needs.
It's a fascinating dynamic.
It really is. And we're looking at a blog post today from April 27, 2026. It's titled, Notes on Haskell Programming, Part 120. Why Haskell Still Struggles with Strings.
Written by a developer named Ang.
Yes, Ang. And that part 120 is key here because Ang has been tinkering and writing about Haskell every single day for roughly 3 months.
3 solid months of just hitting walls and climbing over them.
Yeah, daily logging.
And that daily format is invaluable. It gives us this real-time window into how a developer actually maps brand new, highly abstract concepts to their existing knowledge.
Right, trying to bridge that gap.
Exactly. To eventually grok a really complex system.
Okay, let's unpack this. Ang is working on what should be a totally trivial script. It's a functional stub for an ebook converter.
Right.
So the script takes an input file, like a markdown document, and an export format, say EPUB. And the goal is literally just to output a new string with the swapped file extension.
A completely standard string manipulation task. Nothing crazy.
Right, nothing crazy. So Ang brings in the filepath library to handle the heavy lifting, parsing directories and file names.
Which is standard practice.
Yeah. But to get the target extension formatted correctly, Ang writes this line of code that just looks incredibly strange to modern developer eyes.
Oh, the map to lower line.
Yeah, exactly. The code is let ext equals map to lower. Show FMT. The weird part there is the word map.
It stands out immediately.
I mean, why is Ang mapping over a string just to make it lowercase? In almost any other modern language, you just, call a lowercase method on the string object itself and be done with it.
Right. Well, to understand the mechanism behind that map function, you really have to look at how Haskell fundamentally defines text in its standard library.
Okay, so how does it define it?
So the to-lower function Ang is using, it comes from the data char module, and it's designed to operate on a single character at a time.
Oh, wow. Just one character.
Just one. It physically cannot process an entire sequence at once. And that's because, in standard Haskell, a string isn't a cohesive, contiguous block of text.
Wait, really? Then what is it?
It's a linked list of individual characters. Syntactically, it's represented as char.
Okay, so let me make sure I've got this. It's like you have a wallet full of loose pennies. That's the list of characters.
Okay, I like where this is going.
But what you really want is a crisp dollar bill, right? A proper text string. But every time you want to buy something or do something with the text, you have to count out the pennies one by one using a map function.
That is a perfect way to visualize it. And mathematically, mechanically, that's spot on.
That sounds exhausting for the computer.
It is, because in memory, instead of a contiguous array, it's a total scavenger hunt across the heap.
A scavenger hunt.
Yeah. The first letter tells you where the second letter lives. The second letter has a pointer to the third letter.
Oh, man. So you have to travel all over the memory space just to read a single word.
Every single character requires a pointer to the data itself, plus another pointer to the next node in the list.
So for a 5-letter word,
you aren't just storing 5 bytes, you're allocating multiple nodes scattered everywhere.
why would they ever build it like that?
Yeah, well, you have to remember, in the 1980s or 90s, when Haskell was being formalized.
Oh, right. Different times.
Exactly. Lazy evaluation of text streams was this novel research concept. It made sense then. But for modern UTF-8 processing in 2026, traversing a linked list just to lowercase a word is a massive waste of CPU cycles.
Yeah, you look at that and think, well, just use a modern data structure. And Ang obviously looks at the same thing.
Naturally.
The alternative is data text. If a linked list is the loose pennies, data text is the crisp dollar bill, or like a billboard. All the characters are painted in one contiguous, highly optimized block of memory.
Exactly. The billboard analogy works perfectly for data text, But bringing that billboard into the specific script creates a huge architectural clash.
How so?
Because the replace extension function, the one Ang needs from that filepath library, is old.
It expects the pennies.
It expects the legacy char linked list. It does not know how to read the data text billboard.
Let me guess. To use the modern efficient text type, Ang would have to write a bunch of messy boilerplate just to satisfy the old library.
Oh, it becomes an absolute performance nightmare. First, you import the modern text library.
Right.
Then you take your input string and run a pack function. This iterates through the linked lists and compiles it into a contiguous array.
Okay, so you pack it up.
Right. Then you run the highly efficient to lower function on it. Great. But because replace extension demands the old format, you immediately have to run an unpack function.
You're kidding.
Nope. You have to shatter that contiguous array right back into a linked list of pointers.
Wow. So you're burning more CPU cycles converting the data back and forth than you are actually processing it.
Exactly. It completely defeats the purpose of optimizing it in the first place.
So if they can't change the core language without breaking everything, do they just write a wrapper around the whole thing? How do they survive this?
Well, if we connect this to the bigger picture, the tension Ang is experiencing right here is basically the defining dilemma of mature programming languages.
The burden of legacy.
The paralyzing weight of backwards compatibility. Now, you mentioned a wrapper, and that is actually how the Haskell community addresses this today.
Oh, really?
Yeah, but we should look at Ang's initial reaction first because it's super relatable. Ang argues that since it's 2026, the Haskell maintainers should just bite the bullet, rip out the char type entirely, and make text the default across the board.
Here's where it gets really interesting. Because Ang explicitly compares this to the Python 2 to Python 3 migration path.
Right, the infamous migration.
Yeah, Ang thinks they should just force a hard break, just rip the Band-Aid off. But looking at the history of language migrations, does a massive, painful rewrite actually make sense for a community? Or is Ang just, venting frustration over a file extension script?
I mean, it's almost certainly the latter. Ang is venting. Because the Python 3 migration is the exact reason language designers are terrified of hard breaks.
It was rough.
It was brutal. Python 3 changed how strings were handled at a fundamental level. They made Unicode the default instead of treating strings as raw byte arrays.
Which, conceptually, was the right move.
Conceptually, yes. For the modern web, it was essential. But practically, it broke millions of scripts.
Every library out there.
Entire enterprise applications just stopped working. It took well over a decade to sort out, it fractured the community, and it cost companies untold millions in developer hours.
Just to rewrite code that was already functioning perfectly fine yesterday.
Exactly. You don't just push a button and update a language. You force an entire global ecosystem to pause feature development and pay down technical debt simultaneously.
That is a tough pill to swallow.
Yeah.
But Ang actually maps this struggle to another ecosystem, right? To try to make sense of the friction.
Yeah, Ang brings up Erlang and Elixir.
Oh, interesting. They run on the Beam virtual machine.
Right. And Erlang, which is heavily used in telecommunications, had an identical problem. It didn't have a modern string type. It used what they call char lists, written with single quotes.
So another linked list.
Under the hood, yes, they were literally just linked lists of integers.
I guess because in old telecom systems, everything was just a stream of bytes anyway.
Exactly. The system just saw data streams.
Yeah.
So when Elixir was built on top of Erlang to modernize the whole ecosystem, they had to confront these integer lists.
So what did Elixir do?
Elixir's creators introduced binaries, which you write with double quotes, and these act as modern, contiguous UTF-8 encoded strings.
Oh, nice.
Yeah, and they sandboxed the old Erlang char lists behind a specialized syntax. So the modern way became the default.
Okay, so Elixir managed to make the modern way the default without breaking the underlying Erlang machine. But wait. If an Elixir developer needs to call an old Erlang library for some deep networking thing,
You caught it.
they still have to feed it the integer lists.
They do. They still have to use conversion functions like toTarlist to cross that boundary. The legacy friction is mitigated for sure, but it's never fully erased.
It's always lurking there.
Which brings us back to your earlier point about wrappers in Haskell. Because instead of forcing a Python 3 style apocalypse, the Haskell community uses what are called alternative preludes.
Okay, alternative preludes. Now, the prelude is the default set of tools that loads when you boot up a Haskell file. Right?
Correct. The default prelude brings in that old string-linked list. But an alternative prelude is a community-maintained package that shadows those base libraries.
So it sneaks in front of them.
Basically, When you load it, it exports the modern text type by default, and it uses advanced compiler features, specifically type classes and polymorphism, to create functions that resolve the correct type at compile time.
Hold on. So the compiler looks at the function, sees whether you passed it a legacy string or a modern text, and just automatically routes it to the optimized implementation.
With zero runtime overhead, yes.
Oh, wow. That's actually amazing.
It is. And Ang mentions planning to explore these alternative preludes in future posts. It completely avoids the Python 3 trauma by making modernization an opt-in library rather than a mandated global rewrite.
You know, you look at this whole string conversion mess, and at first you think Haskell's just needlessly stubborn.
Very stubborn.
But that exact same stubbornness, that absolute refusal to let types bend or fail silently, is the very reason it handles application logic like nothing else.
The thematic pivot Ang makes here is brilliant. Because in the exact same code snippet where Ang is battling the ghosts of 1990s string implementations, we see Haskell's error handling, and honestly, it still feels decades ahead of its time.
Let's look at the function signature Ang writes for this converter. It's convert to ebook, and it takes an export format, a file path, and a list of token.
Right, that's just describing the inputs.
But the output is where the magic happens. It returns an I/O action wrapping in either string.
That either type is an algebraic data type. It is the mechanism that essentially replaces traditional exception handling.
Okay, so no try-catch blocks.
No. In Haskell, a function doesn't just throw an error into the void, hoping some try-catch block somewhere catches it. It returns a value that mathematically must be one of two things.
Left or right.
Yes. The convention is that right represents success. So in Ang's function, a success returns right.
And the empty parentheses there just mean the operation succeeded, but it doesn't have any specific data to return back.
Exactly. It just means all good.
Okay.
Now, left represents failure. If the file is locked or the format is invalid, the function returns a left containing a string that describes exactly what went wrong.
Okay, conceptually I get it, but returning an object that says I succeeded or I failed isn't totally unique to Haskell. I mean, what makes this so powerful in practice?
What's fascinating here is how Ang compares this experience directly to Elixir to highlight the difference between a community convention and strict compiler enforcement.
Oh, right, because in Elixir, developers use with block-to-chain operations, right?
Yeah, and the convention in Elixir is to use tuples. So you'd have, value for success and .error, reason for failure.
But in Elixir, the developer has to manually wire the escape hatch.
Exactly.
Like if you chain 5 database calls in a with block, you have to remember to write an else block at the bottom.
Yep, you have to use pattern matching to catch that error, reason tuple, and decide what to do with it.
And if you forget to write that else block,
or if your pattern match has a typo,
right,
the Elixir compiler might just let it through. And then your program throws a matcher and completely crashes at runtime.
Oh, so Elixir really relies on the developer's discipline.
It does. But Haskell relies on mathematics.
Ang points out the Haskell bind operator here. It looks like a less than sign and a dash.
The arrow.
Yeah, the arrow. So in a Haskell do block, you chain your functions together using this bind operator.
And that bind operator is highly context aware. If you write a line like user fetch user id,
you aren't just assigning a variable.
No, you're not. The bind operator is actually inspecting the either context that gets returned by fetch user.
Wait, really? So the MLEs isn't just an assignment operator. It's actually a context-aware unwrapper.
Yes.
So if fetch user returns a left containing an error, the bind operator sees it and automatically short-circuits the entire block.
Exactly. It just bails out. It returns that left all the way up the chain. You don't write an else block at all.
You don't write any error-handling boilerplate?
None. The bind operator handles all the plumbing for you. And if fetch user returns, right, the bind operator unwraps the value, assigns the user data, and just proceeds to the next line.
And because of Haskell's incredibly strict type system, you literally cannot forget to handle the context.
You can't.
The compiler physically stops you from compiling the application.
Yeah.
If you try to use a function that returns an 8 eyes without properly unwrapping it, it literally forces you to acknowledge the possibility of failure.
It's beautiful, isn't it? It fundamentally shifts how developers model architecture. You stop thinking about catching random exceptions.
Right, it's like plugging holes in a sinking ship.
Yeah. Instead, you start structurally defining the boundaries of success and failure as basically mathematical proofs in your type signatures.
I mean, anyone listening to this who has ever tried to pick up Rust or learn Kubernetes or really dive into any highly complex, opinionated architecture, They know exactly where Aang is right now.
Day 120.
Day 120. 3 months of feeling like you are fighting the machine every single day. And suddenly you just start to see the matrix. Aang mentions finally starting to grok Haskell.
Grokking is such a distinct psychological threshold in software engineering.
It really is.
It's that moment you stop translating syntax line by line in your head and you start comprehending the philosophy of the system itself.
You stop fighting the compiler.
And you let it guide you.
So what does this all mean for you, the listener, when you're trying to learn something dense and intimidating? Because the way Aang achieves that understanding is what I find so compelling.
Right. Aang doesn't achieve it by just memorizing Haskell documentation in a vacuum.
No. The entire blog post is this incredible exercise in mental scaffolding.
That is the absolute core of comparative syntax mapping. Aang uses the flawed legacy systems of Erlang to build a bridge to the abstract memory constraints of Haskell.
Right.
And then Aang uses the manual error tuples of Elixir to highlight the automated brilliance of the Haskell bind operator.
It is the cognitive science of learning a complex system in real time. You take the alien concepts, like algebraic data types or linked list strings, and you anchor them to familiar frustrations and known patterns.
That constant comparative analysis is really the only way a human brain can map abstract math into usable engineering logic.
It's how we learn.
Exactly. Aang's struggle with the legacy strings and the discovery of the either type, they aren't isolated technical hurdles, they're the vehicles for that cognitive mapping.
You can't appreciate the solution until you really feel the pain of the problem.
Right. You cannot understand the elegance of Haskell's safety until you've wrestled with the stubbornness of its foundation.
So to quickly recap our deep dive today, we started with the developer simply trying to swap a file extension.
And we ran headfirst into the architectural technical debt of Haskell's linked list strings.
Exactly. We explored why mature languages are totally paralyzed by backwards compatibility.
And how alternative preludes use compiler polymorphism to sidestep the whole trauma of a Python 3 style migration.
Yes, and then we saw how that same rigid, unyielding type system provides this flawless, automated mechanism for error handling.
All through the either type and that context-aware bind operator.
So if you are listening to this on your commute, and you're currently, 3 weeks into learning Go or Rust, or even just picking up a massive new code base at your job, keep Aang's 120-day mark in mind.
Definitely. The legacy friction that is driving you crazy today is the exact mechanism that forces you to understand the architecture tomorrow.
The friction builds the mental scaffolding.
But, this raises an important question, one that really brings our entire analysis full circle.
Let's hear it.
Well, if Haskell's absolute greatest strength is its mathematically rigorous type system, the very thing that enforces safe error handling so beautifully and eliminates runtime crashes, is it possible that this exact same strictness is what makes evolving its foundations so paralyzingly difficult?
Oh, wow.
Is the unyielding architecture that makes the language so incredibly safe also the trap that makes migrating from a legacy string to a modern text format nearly impossible to achieve?
The strictness that saves you is the strictness that traps you. Is evolution impossible in perfectly safe systems?
That's a paradox.
That is a phenomenal thought to leave on. Thank you for joining us on this deep dive. Keep anchoring those new concepts, embrace the friction of the systems you're fighting, and keep looking for that underlying logic. We'll catch you on the next one.